orthogonal frequency division multiplexing, that is OFDM, is a promising multi-carrier modulation techniques that mitigates the effect of. So after that, the frequency division multiplexing. In frequency division multiplexing, as I told, we'll be adding an guard band, which is the gap between two channels. What we are doing is we are using more of the spectrum, but our spectrum is very narrow, right? Like there is some set of frequency band that will be given for mobile communications, data communications, and all. So within that range only, we should be using the spectrum. So that is one disadvantage of frequency division multiplexing. So next is code division multiplexing. So the main disadvantage of that is it self jamming happens, and it's like it decreases um, what we say uh, accuracy when the more number of users are there. So to overcome all this, the best method is orthogonal frequency division multiplexing. So this orthogonal frequency division multiplexing, that is OFDM, is a promising multi-carrier modulation techniques that mitigates the effect of frequency selective fading inherits in high data rate environment. It is a type of multi-carrier modulation scheme based on the idea of dividing the given high bit rate data stream into several parallel low bitrate streams and modulating each streams on separate subcarriers, often called as which we call it as subcarriers. So each subcarrier is modulated with the conventional modulation schemes that can be QAM, PSK, or some modulation technique at low symbol rate. So this maintains total data rate. So this will maintain the total data similar to that of single carrier modulation scheme with same bandwidth. So the main advantage over this single carrier modulation is it has the ability to cope up with the channel conditions. For example, attenuation of high frequencies, narrowband interference, and selective fading, due to which because due to multipaths and all. So we can see this. So this is the if there is one signal and it has been divided into multiple subcarriers. So the subcarriers, you can see the red one is first subcarrier, second is blue color, and another one is purple color. So this is how we can divide a single signal into multiple subcarriers so that we use the spectrum efficiently, and it is also orthogonal to each other. So we can see if we take at this time slot, there is no other signal interfering to this. If we take at this time, there's no. So there will be no signal overlapping each other. So there will be no intersymbol interference as of such. Okay. So this is about orthogonal frequency division multiplexing. Yeah. So the information modulating discrete time. Each user has the different center frequency with the allotted bandwidth. So particular bandwidth will be given, and particular center frequency will be there. So if the carrier signal modulation system has T symbols, then it will take n subcarriers. So you can divide that T symbol into NT, like you can divide the symbol into small chunks. So that's how the OFDM is built. Okay. So yeah, so this is how a OFDM packet looks like. So first we'll be adding a training sequence, which is of two sets. I will tell the advantages of using this two training sequence at start, and then we'll be having a cyclic prefix, and then preamble also I'll be telling in further slides, and then our data, OFDM data. So this training symbols we are using two copies so that the frame detection happens properly. So which in turn helps in correcting the phase and frequency offset of the data. So in orthogonal frequency division, the main problem that might cause is the frequency offset or phase offset. So this will be overcoming using an estimation technique, which I will be going through in further slides. So next is cyclic prefix. So training sequence we know. Next is cyclic prefix. So cyclic prefix is just a copy of symbols of OFDM message. So it helps in avoiding the interference between successive OFDM. It provides some period. It provides periodicity to the OFDM signal. So the linear conversion can be converted to circle conversion. So what it means is, so now we are having some OFDM symbol like this. So let's consider it as packet 1, and it is having some data at full. Okay. So what we do is we take a small chunk of data from backside and we append it at front. So this helps in avoiding the inter-symbol interference, so that even though if the previous packet get interfered with this, so if I say that some other packet is coming in and it's interfering, other symbol is interfering with this symbol, so this can be very vital, like we are losing some data here. So instead of sending only one packet at a time, what we do is we create a copy of that, so that we have the bit of information at last, even though the bit is corrupted at the beginning of the packet. So this is the use of cyclic prefix in OFD. Next is the preamble. Preamble is nothing but a unique uh, keyword that we give to the packets. For example, each of us will be having the unique phone numbers, right? So similar to that, we'll be giving an unique code word for each packet, so that the receiver can differentiate between the different users. So that is the use of preamble. So next is the transmitter, how it's been designed. So first the message data will be there, source coding we do, and channel coding, standard modulation, that is QPSK, BPSK thing, and the OFDM modulation. So in OFDM modulation, I will be going through what are there inside that. And then we packetize, upsample, pulse shape, and RF front end, that is USRP, will be transmitting it through. So as we can see, all are similar to that of CISO code. The only extra thing that has been added is OFDM modulation. Okay, so this an extra bit in OFD. Next is inside, yeah. So this is how the OFDM block looks like. So first we'll be taking in the from the standard modulation thing, like we after converting our bits into symbols, we'll be making that symbols into a parallel manner. So after converting that symbols into parallel format, we insert key null tones. Null tones is nothing but the guard that we add in between two subcarriers, so that there will be orthogonality between each other. So if we are having a symbol like that, so there is some bit of null tones that we'll be adding in between each subcarriers, so that they do not overlap each other. And then we do is endpoint IFFT and insert cyclic prefix, and then parallel to series, and then we transmit through the USRP. Next is, yeah, inserting null tones. So as I told, at the we will be inserting it at the edge of the well, like starting at the end, and to avoid interference, as I told before. And yeah, this will be removed at the receiver side. So this and all I'll be going to in further slide. Okay. So IFFT. So why we do IFFT in orthogonal frequency division multiplexing? So initially, what they were doing is to get to, we have divided the message into multiple sub packets, right? But it will be having different center frequencies. So to do that, uh, uh, it would have taken n number of multipliers and n number of signal generators. So you can see here, this is the traditional what modulation orthogonality building technique. So there are different multipliers, n number of multipliers are there, along with n number of signal generators. And then we sum it up, and then we transmit to a channel. Again, at receiver side, we want to demodulate, we multiply it with the different signal generators, like different carrier frequencies, and then we take out the data. So instead of doing this, there is a technique called as IDFT, where the time domain signal is converted into frequency domain with different center frequency. So with change of n, like with change of k, different carrier signal has been will be allotted. So instead of using n number of um, modulators, we can use a single um, regional signal processing technique to overcome this hardware compatibility. So that's why we use IFFT in orthogonal frequency division multiplexing. Next is the receiver. So in receiver, the passband signal will come in. That is RF front end is nothing but USRP. Match filtering happens, which is similar to that of CISO code, and simple timing recovery, downsampling, and OFDM demodulation, and again the standard demodulation, that is QPSK, BPSK, what we have selected. Symbol to bits mapping, conventional decoding, and source decoding happens. So next is how the OFDM demodulation has been designed. So similar to that of transmit in the CISO code, we do first what symbol timing recovery, right? So in this symbol timing recovery works well, but there is a chance that The signals, the subcarriers that we receive, right? There might be a chance that they might overlap each other. And uh, for example, like if the signal should be like this, instead of this, the this carrier signal would have been moved something around left side. This happens because whenever we are working on with USRP, right? So there might be a chance that the local oscillator, which is inside the USRP, instead of if we fix for 1 gigahertz, there might be a chance that it will give out 1.1 gigahertz instead of 1. Right? This 1.1 gigahertz, like zero point 0.1 gigahertz change, difference will impact more on the OFDM because all are tightly packed, right? Even though even there is a small mismatch between the carrier signals, uh, the decoding might not happen. So to overcome that, we do first frequency and frame synchronization, and then we extract the training sequence from that, so that we do channel estimation to overcome this ISI effect and retrieve the mixed bits inside the packet. Then we do series to parallel conversion, which is opposite to that of OFDM modulation. Series to parallel conversion and point FFT, frequency equalization we do, and then remove null tones and parallel to series conversion. So this is how the OFDM demodulation block works. So next is how the frequency and frame synchronization happens. So this is similar to that of transmitter, similar to the CISO frame synchronization, where we take for a number of samples and which is having the highest energy, we will take that as the sample rate, like sample, we will take that sample. So this is how it's been done in the OFDM as well. So next comes the Smith-Cox algorithm, where we will be estimating the frequency offset and the phase offset as well. Because in OFDM OFDM transceiver, even as I told before that, even though if there is a small change in frequency, the subcarriers might overlap each other. So to overcome that, we'll be doing an estimation technique for estimation of frequency offset and all. So what we do first is we do a correlation with that of the training sequence. After that, we uh, compute the average received signal power. So average signal power we will be taking out, and then we do an the like compute like R of D divided by P of D we get, and then we determine the M of D what we are getting from this. So after doing that, we'll be taking out the phase of that. So by this we'll be getting the frequency offset, and by this we'll be getting out the phase offset. That